Welcome to the solutions to problem set 12. Very sorry that it was so long and intricate, but I think this subject can only be learned through many exercises. And this will be a foundation for all of your studies in math, be it algebra or analysis or whatever. You always need a firm grasp of the concept of a map. So we start with functions we know from high school, and we have to decide if those are injective or surjective. They can of course be both. So let's start with the pedestrian approach by checking both separately. So injectivity, let's say we have f of x equals f of x prime. This means by definition that 2x equals 2x prime, and then of course I can cancel the 2 and I'm left with x equals x prime. So this map here, or this function, is injective. And we only need this implication, so it suffices to do it in this way. So by simple algebraic manipulation you find out that it is injective. It's also important here to think about the graph of f, which is a line going through the origin with a slope 2, and clearly no element here gets hit twice. So you can see the injectivity at the graph. Or another way to visualize it is you imagine parallel lines parallel to the x-axis, and if they intersect the graph at most once, then the function is injective. This is a very useful way to think about injectivity when we have functions that we can actually plot like that. So surjectivity. Now here you have to think about the following. Does every line, every parallel line to the x-axis intersect the graph at least once? Well, obviously, this means surjectivity when looking at the graph. For the beginning, let's write it down. We take an element of the codomain and we have to find an element in the domain such that it gets mapped to this y. Now, this can always be done. Simply take y over 2. That's it. A more elegant way to do this would be you do this on an extra sheet of paper and you say, well, f of 1/2 y is 2 times 1/2 y is y. So you do this before and then you just write down, well, this can be done. Simply take this here to be x and then it works out. All right, so this map here, or this function, is both injective and surjective, so it's bijective. Now let's do this more elegantly using proposition 15. We simply find the inverse map. And this is exactly what we did here. You start with y equals f of x, then you solve for x, and then you interchange x and y, and then you have the inverse function. This ideally you should have learned that in high school already. So we say this map here is the inverse function. And then we automatically know that f is bijective, so it is both injective and surjective. Now to prove that, we have to prove that this composition is the identity of R. So let's do that. So this means by definition that. So by definition this means that, by definition of f, And now f inverse is the map that takes its argument and divides it by 2. So we end up with x. So this is the identity of R. And now, to make it perfect, this is true for every element of the domain. And this means that this map here is indeed the identity of R. Now the other way around is almost the same. You do that on your own. So this here implies that this composite is the identity, and similarly the other way around. Or abstractly, you could argue that the bijective maps from R to R are a group under composition, and there we already know that a left inverse is automatically a right inverse. But I think it's okay to just say, well, it's almost the same. So this shows more elegantly that f is both injective and surjective. Okay, part B is this here, injective or surjective. You know from high school that the graph of this function is the normal parabola, I can't seem to pronounce this word, the parabola. This is clearly neither injective nor surjective. So to show that it is not injective, one counterexample is enough. You can see it here. -1 is not the same as 1, but -1 squared is the same as 1 squared. So this contradicts injectivity, because if it were injective, then those would have to be different. They're using the contraposition of the injectivity property. Or you can say this way, these are equal, but those are not. So it's not injective. And here in the graph, you can see that this red line here intersects more than once, and then the function is not injective. And it is neither surjective, because this line here does not intersect the graph at all. So in our terminology, -1, for example, is not in the image of f, because you can't find a real number that squared gives you -1. This shows it is not surjective. But all these problems vanish when I change the domain and the codomain. If I simply regard this, as a map from R sub 0 plus, meaning the non-negative real numbers, to itself, then I only have the right branch of this parabola, and this also is gone. And then it clearly is a bijective function. And here is its inverse. It is simply the square root function. So it's very important to understand that these here, these properties, rely heavily on the domain and the codomain. All right? So this here is injective and surjective. We could do it by foot, or we simply give the inverse map. This would be the graph of the square root function, and maybe you remember from high school that if those two are spiegelsymmetrisch, are mirror symmetric to this diagonal with slope 1, then the functions are inverse functions of each other. So my claim is that this here is the inverse function. And behold, those are different domains and codomains. So, and now we really have to be careful. So we want to show that this composite here is the identity of the non-negative real numbers. So f inverse of x here by definition is x squared. F is the square root function, so we have this. And this here is not true in general. So here, in general, the square root of x squared, shout out to my students at school, I always try to teach them that, is not, the square root of x squared is not x, but the absolute value of x, because by definition the square root is a non-negative number. So if x is negative, this cannot be true, that the square root of x squared is x. But now our domain is such that we only have non-negative numbers, so this is the same as x, so this is the identity of r sub 0 plus of x. So this shows, because this is true for all x greater than or equal to 0, that f composed with f inverse is the identity. Okay, the other way round, we have this here, f inverse composed with f of x is square root of x and then squared. Now here we don't have to be that careful, but first of all, because x is non-negative, the square root exists, and then by the property of the square root, by definition, the square root of x squared is x. So this composite as well is the identity, thus showing that indeed they are inverse functions of each other, proving that f is bijective, so it is injective and surjective. And if you try to do this by foot, both separately, you also have to be careful about this stuff here. But I'm gonna leave that as an exercise for you if you want to do that the other way. All right, part D, the absolute value function from the real numbers to the non-negative real numbers. You should know from high school that the graph of this function looks like that. Is it injective? Clearly not. Same argument as with the square function. This line, for example, intersects the graph twice, so it is not, this is the abbreviation for not, it is not injective because the function, the images of those two are the same, but the arguments are not the same, so it is not injective. Is it surjective? Clearly, because we restricted the codomain to the non-negative numbers. So if I take any non-negative number, sometimes if you're lazy, you can write it like that and then go on in this direction. Y is an element, an arbitrary element of the non-negative real numbers, and have to find a pre-image under f. But this is trivial because for non-negative numbers, the absolute value is just the number itself. So this here clearly is f of y. So we have shown that every y in the codomain has a pre-image under f. So it is surjective but not injective. Okay, next example, the hyperbola of order 1. X maps to 1 over x. This here is r without the 0. Domain and codomain are the same, and just by looking at the graph we should realize that f is bijective because all the parallel lines intersect exactly once, and the x-axis itself is out of the picture because we took the 0 out of the domain and codomain. So this should be a bijective function. Then it must have an inverse function. And this is maybe surprising at first look. This function is its own inverse. If you know about the geometry of inverse graphs, as I've mentioned before, to get the inverse graph, you have to reflect this graph here about this axis here with slope 1, and then you get the same graph. I did not draw perfectly, but I think the idea should be clear. So my claim here is that f is its own inverse. So f composed with itself should be the identity of r star. Or you could either check injectivity and surjectivity by foot like that. Please do that if you're a beginner. I will only do this. So this is f of x. This is f of 1 over x. And again, this is 1 over x. But this is just x. You multiply with the Kehrbuch inverse fraction. And you end up with x over 1 times 1, which is x. So this is the identity of r star of x, showing that indeed f is its own inverse. And of course, this I only have to check once because this is the same as f composed with f if I switch the order. So that's a nice elementary example of a function that is its own inverse. And therefore, this f here is bijective. Okay, last part of exercise number 1. We take this function from the integers to the even integers. X gets mapped to 2x. This clearly is well defined because 2x is an even number for any integer x. Now, I claim that f is bijective. This is easy to prove, but what are the ramifications of that? I think everybody would naively say there are twice as many integers as there are even integers, right? Because we leave out all the odd integers. Well, this is not true, because this here actually is a bijective map from the integers to the even integers. So there are as many integers as even integers, as strange as this may sound. In exercise number 3, you will, or we together will find a bijective map from the natural numbers to the integers. So here's the same. They both have the same cardinality. They are what is called a countably infinite set. And it is not true that there are more integers than even integers, as strange as this sounds. And if you look closely, this is exactly the same map as in exercise A, only restricted now to the integers. Its domain are not the real numbers, but simply the integers, but the map is the same and the inverse is the same. So CA, in part A, we already proved that these are inverses. And here you have to be careful if this is well defined, if this here lies actually in the integers, because if I plug in 3, I would have 1.5, which is not an integer. But by definition, we start with an even integer. This exactly means that this number divided by 2 again is an integer. So this is a well-defined map. You should write that down. But the proof that those are inverses is exactly as in part A. So, as strange as this may sound, this here is a bijective map. You'll have to get used to that. All right. So in exercise 2, we have 2 finite sets that have the same number of elements. Special case would be a map that goes from A to itself, A being a finite set. So I think here proof by picture with explanation should be enough. We have an injective map. So a map must assign to each element here one unique element there. So for example, this here. Now if f is injective, this here can't happen. So I have to map this here to another element. And again, this here can't be mapped to one of those, because that would contradict the injectivity, though there's only one point left. And we see that is automatically surjective and, of course, then bijective. Okay? This is for injective f. It's easiest to argue by way of contradiction. Assume we have a surjective map that is not injective. What would happen? If it is not injective, there are at least 2 elements here that get mapped to the same. But then automatically at least one element here cannot be hit because it's the same number of elements, right? So then G would not be surjective in contradiction to our assumption. It is surjective, and that is already it. Now good luck with writing that down in your own words. I hope I explained the idea well enough. If you have to hand that in as an exercise, fill in some words and hope that these pictures with the words are enough. I'm not going to do that here on the blackboard. But it's important to remember that for finite sets that have the same number of elements, an injective map is automatically surjective and then automatically bijective. So it suffices to check one condition. If I have a map between finite groups that have the same number of elements and it is injective, I already know that it is bijective. This is often useful.